So, okay, before I continue, I forgot, sorry. In gravitational potential energy, the one that is related to the object's position, we're going to be using a formula. This is the formula that we're going to use for potential energy, gravitational, okay? Gravitational potential energy. G is for gravitational, and the formula is mass times gravity times the height where the object is located. Okay, so this is mass, this is gravity, and this is object's height. Okay, now for elastic potential energy, this is the equation that we're going to be using. Potential energy elastic is equal to 1/2 or 0.5, I prefer the decimal, 0.5 k x to the second power. Now that k is a constant, and this x is another value that I will specify here. Now, the letter k is what we know as constant of elasticity. Okay, let me compare two objects. Take your pencil and take a rubber band. What object is more elastic?
The rubber band.
Of course, the rubber band, okay? You can alter the shape of the rubber band easily, while the pencil not so easily. And if you bend the pencil, it's going to break. And the rubber band is going to get stretched a lot before it before it is broken. Okay, so how elastic or stiff an object is going to be measured by this constant of electricity. Okay, and the other value that you have to consider for the second equation is x. X refers to a distance, but it's not an whatever distance. It's a very important distance. It could be the distance um, that an object is stretched or compressed. Okay, so for the elastic potential energy, we're going to consider those values, but don't worry, this constant, this k, is going to be given in the problem most likely. Okay, and also x. All you have to do is apply the formula. So now these are the two equations that we're going to use for these two topics. Okay, so let's work with one example. It says potential energy. Who wants to help me to read this problem?
Okay, potential energy. When a 2 kilogram mass is attached to a vertical spring, the spring is stretched 10 centimeters such that the mass is 50 centimeters above the table. A. What is the gravitational potential energy associated with this mass relative to the table? B. What is the spring's elastic potential energy if the spring constant is 400 newtons per
Meter.
mass, I think, meters?
Yeah.
Okay.
Mhm.
And there is C. What is the total potential energy of this system?
Okay, thank you, Fred. So, with this kind of problems, the first thing that we need to do is actually to know how to gather the information. So these are the two equations that we are using. Okay, these are the two equations that we are using. So that means that we need to gather this data from the word problem. So the first that is given is the mass. It says that this object has a mass of 2 kilograms and is attached to a spring. Okay, now this spring is stretched 10 centimeters such that the mass is 50 centimeters above the table. In the first part, it says what is the gravitational potential energy associated with this mass relative to the table. So in the first part, we need to get gravitational potential energy relative to the table. In part B, it says, what is the spring's elastic potential energy if the spring constant is 400 newton per meter? So in the second part, they're asking you to get the elastic potential energy if the spring constant is 400 newton over meter. And in the part C, it says, what is the total potential energy of this system? Total potential energy of the system. Okay, so all that what I highlighted is the given information in the problem. But sometimes I will also need a sketch, a physical representation of what is going on in this problem. So this is what I'm gonna do now. I'm gonna focus on this problem. So I have a table. Okay, the table is important because in the first part it says that I need to find the gravitational potential energy that is relative to the table. So that's my table. Okay. Now above the table I have the spring. Okay. This spring is coming from the probably from the ceiling or for whatever structure that is above the table. So I have my spring like that. Okay. So this is the initial situation. You have a spring at rest or a spring without anything. Okay. The spring alone. And what you know is that you are going to attach a mass in the end of this spring. So the second situation that will occur is this one. In the second part or the final part of this situation, you're going to add to attach a mass to it. Okay? So what happens when you put a mass in the end of the spring? What do you think is going to happen? What is going to happen to the spring?
It's going to stretch.
It's going to stretch. Okay? Okay, so I put the mass on it and the spring got stretched. So initially my spring was at this point. Okay? This was my initial spring uh, final part for that thing. And all of this distance is the distance that it got stretched. This is the distance that I call x. And this x, according to the problem, it says the spring is stretched 10 centimeters. Okay, so this is equal to 10 centimeters. Now, information in the problem says that this mass, okay, it is 50 centimeters above the table. So from the table to the mass, I have a distance of 50 centimeters. And this distance is relative to the table. This distance I call it h, or the object's height from the table is 50 centimeters. So this is the situation that is going on in this problem. You can also say that the spring has a constant of 400 Newton over meter, but it's not necessary that you include it in the sketch. But you can put it if you want. Now take a look at the units where the constant is given you. It's giving you newtons and it's giving you meters. Meters. And x is given in centimeters and h is given in centimeters. So we have different units. The first step that we will need to do, we will need to perform a conversion. There, your camera must be turned on. Thank you. So I have my sketch. Okay, I have my sketch. And I will start writing the given. The mass is 2 kilograms. The x, or the distance stretched from the spring, is 10 centimeters. As we already defined, this should be in meters. Okay, so we will need to perform a conversion over there. We know that the mass is located 50 centimeters above the table, so this is going to be h, and this is 50 centimeters. Again, it must be in meters, but remember, this is above the table. In part A, the problem is asking you to find the gravitational potential energy. So PEG is unknown, and it says relative to the table. Usually, the gravitational potential energy is taken from the ground. Okay, it's taken from the ground. So if I'm on the ground, my gravitational potential energy is going to be zero, porque no hay una distancia del suelo. But here the problem says that you need to get the potential energy just relative to the table. So the table is going to be our reference point. Okay, va a ser nuestro punto de referencia. Okay, the table. In part B, it says, what is the elastic potential energy? PE elastic is unknown, but they're giving me a spring constant. The constant is given with the letter K, and it is 400 Newton over meter. And in part C, it says, what is the total potential energy of the system? So I need to get the potential energy, but the total potential energy is unknown. So this is how I organize the data, and from this I will start working. The first part that I will work on is going to be in the conversions, because my distances must be in meters. So my step 0 will be to work on the conversions. Now, who remembers how many centimeters do you find in a meter?
100 centimeters.
Exactly. 100 centimeters are inside 1 meter. So we say x, which is equal to 10 centimeters, we're going to multiply times the conversion factor, that is 100 centimeters below there are in 1 meter. And below because they need to be in opposite sides. This will give you 0.1 meters. H is 50 centimeters. You multiply times the conversion factor, that in 1 meter you have 100 centimeters. You cancel centimeters with centimeters, and this gives you H, but in meters, equals to 0.5 meters. That is going to be the step 0. Now, I'm going to work in part A. In part A, I need to find the G, okay? G for gravitational potential energy. So I'm going to work on the first part. That says in A, I'm looking for PEG. According to the formulas that I gave you, PEG, we can get it like this, okay? PEG is equal to mass times gravity times height. So I'm going to copy the formula, okay? And then I will plug in the givens. The mass is given in the problem, the gravity no, but you know the value of the gravity. So it is an implicit given. And you know the position of the object. So we just need to apply the formula. This is 2 kilograms. This is 9.81 meters over second square. And height is 0.5, yeah, 0.5 meters. How much is this?
It is 9.81.
9.81. Now, in what units do we represent energy?
In joules.
In joules. So PEG is equal to 9.81 joules, like that. With this, we finish the first part. We continue with part 2 of the problem, that is, get the elastic potential energy, or PEE. I don't know the formula, but I know I have them here. It says PEE is equal to 0.5 kx to the second power, or 0.5 constant of elasticity, stretch distance, raised to the second power. Okay, I have my formula over there. 0.5 is part of the formula, k is given in the problem, and the stretch distance is also given in the problem, so we can apply the formula, and we say okay, K is the constant of elasticity, which is here, 400 Newton over meter. X is the distance that the object is stretched or compressed. So here the problem says that the spring is stretched 10 centimeters. So those 10 centimeters are by X. But remember that they are written in meters, so it is 0.1 meter raised to the second power. How much is this?
It is 2.
I got to
2, and because we're talking about energy, energy is given in joules. Now, in the last part, it says that I need to get the total potential energy of the system. But I didn't give you any formula for total potential energy, so let me see. I need to find the PE total. Now, let's take a look. Well, according to the map that I gave you about potential energy, it says that the potential energy is equal to gravitational and elastic potential energy. So I can transform this map into an equation. I can say that potential energy, I can say that the potential energy is the addition of these two potential energies, gravitational and elastic. So I can say that the total potential energy of the system is equal to the gravitational potential energy plus the elastic potential energy. I input the givens. Gravitational, we got 9.81 joules, and elastic, we got 2 joules. In total, you get how much?
11.81.
11.81 joules. So as you can see, even if I didn't give you in the beginning the formula for total potential energy, if you just apply the principle of how the potential energy is classified, you know that you had to add the two energies that you got in this problem. So these are the equations, those in black color, okay? And this is the one for the total. Ready?
Miss, the problem gives us like 2 units of length, which are 10 centimeters and 50. How do you know which one is the distance and which one is height?
Exactly. That is the best question that I received today. Thank you for asking it. And X will include words like stretched or compressed. Okay? Those are keywords to know that I'm talking about X. Now, in this case, the value that is next to stretch or compressed is the value of 10. So I know that this is X. This is a way to know it. Another way is, for example, this one, the mass. The mass. Where is the mass located? Where is the mass located? It says that the mass is above the table. Okay? Now, where above the table? Exactly where is located 50 centimeters above the table. So the answer, yes, the answer to the question where is located is X. Answer is H. Okay? And the answer to the question um, how much is stretch or compressed is going to be X. X is relative to the elasticity. So those two words are going to be implicit. stretch or compress gives you x, and the other value, the one related to position or location, is going to be h. I don't know if this answers your question.
Yes, miss. Thank you.
So remember, x is going to be followed by or preceded by stretch or compressed, and height is going to be more related to location. Okay. For example, if I say a spring is compressed 20 centimeters and the mass that is attached to the spring is 2 meters above the ground. What is x and what is h? I
Can you
said,
repeat, miss?
I said, I'm gonna type it here. Okay, is 2 meters above ground. So what is x and what is y?
X will be 20 centimeters and H will be 2 meters.
Exactly. So one is related to position and the other one is related to elasticity. That's how you recognize the two values. So today I will send you exercises similar to this one so you can apply the formulas. And on Wednesday that we have the quiz, there are coming 4 topics: work, kinetic energy, gravitational potential energy, and elastic potential energy. The 2 topics from today and the 2 topics from last week. Okay, so remember to write those equations in an index card. Separate those index cards by the titles: work, kinetic energy, elastic energy, potential energy. Okay, separate by tabs, and you're gonna be just fine. I'm gonna send you homework today. Also homework for chemistry. 10 exercises for you to balance chemical equations, and tomorrow you ask me, Miss, can you explain the number 2 and the number 3, or whatever doubt you have about balancing is going to be for tomorrow. Okay, so in chemistry, it's just common balancing chemical equations, and for physics, it's the last 4 topics. They're actually just 2 topics, okay? Just work and energy. Those are the 2 topics. But you know, energy has kinetic, gravitational, and elastic energies. That's why it seems like a lot, but it's not. Just remember to perform conversions every time you have data which is not in meters, for example. And that's it. And here in this presentation, I will write the formulas already isolated for you to keep them with you.